Good morning, ladies and gentlemen, and Happy New Year. Let's go ahead and take a look at our Bellwork exercises today. We know that as we go to evaluate an indefinite integral, we're looking for an antiderivative function. And initially, I'm thinking a fraction could be natural log, because the derivative of natural log is 1 over the function times the derivative of the function. But that lonesome 8 up there, right, can't be the derivative of that bottom quantity, x squared minus 10x plus 9, because there's no x in it. So I'm thinking inverse tangent, because I got an x squared. But inverse tangent is 1 plus input squared. And here I've got this 10x linear term in there as well. And so it's not looking like inverse tangent either. That's okay. We can factor that denominator into a product of linear factors and then rewrite this integrand using partial fraction decomposition. So I'm going to go ahead and do my super duper rewrite here. I'm going to factor that denominator. And we have several resident expert factors in here, so I'm going to go ahead and call on you to share your linear factors. So get ready. X squared minus 10x plus 9 factors into, Riley?
X minus 1 and x minus 1.
X minus 1 and x minus 9. And I know, right, guaranteed we'll be able to write that as a sum or difference of individual simpler fractions, right, in accordance with our partial fraction decomposition. So I know that this is given by some constant a over x minus 1 plus some constant b over x minus 9. So if I can just figure out what those constants a and b are, I'll be able to rewrite that complicated fraction as a sum or difference of individual less complicated fractions, and then looks like natural log, right, to integrate. So that's the deal with partial fraction decomposition. All right, so I'll go ahead and create a common denominator. If I were to create a common denominator, this first fraction would need an x minus 9, right, over x minus 9. So I'll go ahead and rewrite this as a times quantity x minus 9 plus b times quantity. This guy would need an x minus 1. I know that that must equal the numerator 8, and I'll purposely choose x values to make it easy to find those constants a and b. And so what would be a good x value to choose? Kobe? 9. Down. I'm going to let x equal 9. And if we let x equal 9, the a term will drop out, and I'll have 9 minus 1 is 8b equals 8. Therefore, I know b must be 1. Or another convenient x value b. Courtney?
1.
Cool, thank you. So if I let x equal 1, then this b term would drop out, and 1 minus 9 is negative 8. A equals 8. So now I know that a equals negative 1. Yes, which means that all that algebraic work was simply so I could rewrite my original as the integral of a is negative 1, so negative 1 over x minus 1, plus b is positive 1 over quantity x minus 9, and that's equivalent to the original fraction. Raise your hand if you had the rewrite correct. So who had the rewrite correct with the constants? Oh, then we're good to go. What antiderivative rule will follow that? Brendan?
Natural log.
Natural log, absolutely. So I just need the derivative of that function. In each case, the function on bottom's derivative is 1. And so, grace by golly, we did get to do this 8 finally that we were hoping for last time. So I recycled it, and now we get negative ln of x minus 1. Where should I go? I guess down here. Negative ln absolute value of x minus 1 plus natural log absolute value x minus 9. Close bars plus c. Awesome. So raise your hand if you got all the way to the end. You got all the way to the end? Hey, that's great news. Nice work. What questions do you have about the first one? Same process. So I scan and I'm thinking could be natural log because the derivative, right, of that x squared term on bottom would kick out a 4x and I have an x on top. But it's not just plain Jane x, it's a quantity, 5 minus x. And so I think is the quantity the derivative of 2x squared plus x minus 1? No, that would be 4x plus 1, and that's not related nicely to 5 minus 1x. And so it's not looking like natural log. Inverse tangent looks out the window too because I've got that linear term, that 1x in the middle. And so again, I'm going to try partial fraction decomposition because the degree of my numerator is less than the degree of my denominator, but the top is not acting as the derivative of the denominator function. So we'll go ahead and do our rewrite. I'm going to go ahead and factor the denominator into a product of linear factors. And what did you get for this factorization? Marissa?
2x minus 1 and x plus 1.
Raise your hand if you had the same factorization. Did you get the same factorization with the signs? Because then my outer product 2x minus x is the 1x positive. Good job. All right, let's go ahead and rewrite that then as a sum or difference of simpler fractions. So I'm going to have a over 2x minus 1 plus b over x plus 1. If I were to create a common denominator, this first fraction would need the x plus 1. The second fraction would need quantity 2x minus 1. And together, right, that must equal 5 minus x, the numerator. Great. Convenient x value, what do you want to use? Sophia?
-1.
I'm down. Let's let x equal -1. Thank you. In doing so, the a term drops out, and I get 2 times -1 is -2. Minus 1 is -3, so -3b equals 5 minus a -1 is 5 plus a positive 1 is 6. Therefore, b must equal -2. Raise your hand if you had b is -2. Did you get that? Yes! That's great news. Let's let x equal, what do we do for this one? Danny?
X
1/2. So 1/2 would make the b term drop out. Good job. And if x is 1/2, then 1/2 plus 1 is 1.5 or 3/2 a is equal to 5 minus 1/2 is 4.5 or 9/2. Now I can go ahead and solve. It looks like 3/2 a equals 9/2 means that 3a equals 9. So a must equal 3. Is that right? A equals 3. Yes?
Yeah.
Woohoo! So all that, so that I can rewrite my original as a is 3, so 3 over 2x minus 1 plus, and b is, sorry, minus 2 over x plus 1. And a quick check, who got the rewrite? So did you get the rewrite with the signs right? Oh, good. And then we're good to go again. We'll do natural log. This time we need to provide for the derivative of that bottom quantity, and so we do need a 2 canceled out by a 1/2 times 3. I'm getting 3/2 for that first, so I'm getting 3/2 natural log 2x minus 1. Is that right? And then minus 2 natural log of absolute value of quantity x plus 1 close bars plus c. And an equal sign, and PDFable. We're striving for PDFable always. Gotta have a goal. Awesome. And raise your hand if you get number 2. Tyler.
Where do you get the 3/2?
Great question. So, in general, right, we've got a quantity bound to the first power, so I'm going natural log. But in order to do natural log, I need to provide for the derivative of the function because my derivative words are 1 over the function times the derivative function, so I need a 2. But I didn't have a 2, I had a 3. Right, so I need a 2, and then cancel it out with 1. Does that make sense? Cool? Yes. All right. Integration by parts. Whoa the pony, right? 1 and 2 are indefinite integrals. Number 3 is a blast from the past. We're just taking a look at a limit evaluation. And so what's our first, right? Our first strategy when trying to evaluate a limit? Direct substitution to see what we're working with. So the first thing I'm doing is I'm going to let x go to infinity and see, right, what that quantity, that expression is doing. And I'm getting x squared would go to infinity. And e to the negative x would go to 1 over e to the x. 1 over e to the infinity is, e to the infinity is infinitely large, so 1 over infinitely large is going to 0. So I'm getting infinity times 0. Is this a determinate or indeterminate form? You guys, a long time ago, right? We did this here too. So can we tell what this is just by looking at it? No. Remember, 0 times infinity is our single indeterminate product. 0 times 0, no problem. Infinity times infinity, no problem. Right? Plus or minus. But infinity times 0, we've got our battle going on. If the first one goes more quickly, it'll pull the overall value towards infinity. If the second quantity shrinks to 0 more quickly than the first one grows, then it'll pull the overall value of the product to 0. Or is there some balancing act and we get it constant? So what do? Well, we have to write that indeterminate product as one of the forms that authorizes the use of L'Hopital's. So what's our indeterminate form that authorizes the use of L'Hopital's? Tyler?
0 comes infinity.
But that's indeterminate, but I'm saying, how do I need to rewrite it? Which indeterminate forms authorize the use of L'Hopital's?
Oh, one over the other.
Yes.
What's that one?
A quotient.
Yes, the
Infinity over infinity, or 0 over 0, right? Both of which authorize the use of L'Hopital's. So we need to write this as a quotient, right? A quotient, and see if then it authorizes the use of L'Hopital's. So what will we do? We'll keep our limiting expression. The limit as x goes to infinity, and I'll rewrite this as x squared over e to the positive x, because a negative exponent doesn't mean negative answer, it means reciprocal. Now I'll let x go to infinity and see that we indeed generate an indeterminate form, an indeterminate quotient that authorizes the use of L'Hopital's. Isn't this infinity over infinity? Yes? So we get infinity over infinity. So I can go to the hospital. And I'll rewrite this now as the limit as x approaches infinity of procedurally L'Hopital's is not the quotient rule, right? It's take the derivative of the top, take the derivative of the bottom separately, rewrite and try again. So I get 2x over dx. And trying to evaluate the limit yields indeterminate form yet again. But I see the end in sight. I know this will chunk down now to a constant, so that's the last time I'll have to do that. And again, I'm showing the h. That's not an AP thing. That's just so that I know where you're doing L'Hopital's rule. And I'm getting the limit finally as x approaches infinity of a form that's not indeterminate. 2 over e to the x, right? I know that this is going to be the end of my differentiation. As x goes to infinity, I get a constant over infinite quantity. Constant over infinity, is that determinate or indeterminate? Determinate, and the result is 0. So that exists and equals 0. Raise your hand if you get all the way to the end. Did anybody get all the way to the end for 0? Great. And so today, right, we're going to be dealing with some infinities, right? Some infinities and infinite forms as we look at improper integrals. And so I'm pretty excited about that. Again, this is our last new topic in Unit 4, and then we'll be having our test on Monday. All right. Let's go ahead and pause the recording. We'll take care of our OTL passing. Okay, ladies and gentlemen. So for our introduction and anticipatory set today, I'd like to investigate the graph of y equals e to the negative x over 2. And I'd like to pose the question, right? Would it be possible to find the area in between this function, right, and the x-axis in the first quadrant, the entire first quadrant? And so everybody, let's go ahead and take a look at this graph. And we're going to set our window so that we get a nice picture here. Let's do e to the, and up in the exponent we want negative x over 2. And let's go ahead and set our window so they get a nice picture. Maybe we'll do negative 1 to 10 and negative 0.25 to 2.25. Oops. I want to scale 1. And we'll see what that looks like. So here comes our e to the negative x over 2, everybody. Yes, yes? Okay. So we're going to pose a familiar question in terms of area. Can we find the area underneath the curve? Yeah, we've been doing it for 2 years. We're going to find areas underneath curves. It's just we're going to extend this region to not just be in between, 0 and 3 or 0 and 10, but 0 and, well, the first quadrant, how far does that go? Forever, right? Right? Forever to infinity. But I want you to look, right? We could easily find the area in between the curve on 0 to 1. That would just be this portion. And that'll just be right. And couldn't we also find the area of the region in between 1 and 2? That would just be that part, right? And then in between 2 and 3, and so on and so forth. And so, while part of me thinks, no, we can't go infinitely far, right? Another part of me thinks, well, yeah, just over and over again, we can continue to find areas of the next portion, the next portion, the next portion, you know, and if we were to sum all those up, right, couldn't we get the total area underneath the curve in the first quadrant? And so here we've kind of got this battle going on, and I've got it's an interesting question. So what we're going to do is we're going to use calculus. As you've seen, right, the limit has been the foundation of each of the main processes in calculus. Our limit first acted, right, as the limit of a difference quotient to give us the instantaneous rate of change. Later, our limit acted as letting the number of rectangles go to infinity to fill up the space entirely, right? Now we're going to use the limit in a different way. We're going to let the limit on my upper bound of this definite integral go to infinity and see if we can't find the exact area here. So this is an interesting question. So in general, old school, the area in between a function f of x on an interval a b is simply the integral from a to b of f of x with respect to x. In this case, however, oh boy, we'll just leave it. In this case, however, we're going to go ahead and let that upper limit b go to infinity, right? And so we're going to let that upper limit b go to infinity because we wanted the area underneath the curve in the entire first quadrant. And so we're going to go ahead and use this as a starting point, but we really want that b to go to infinity. So we're going to do the limit as b goes to infinity of, and in the first quadrant, we'll allow it start at x equals 0. So we know that one. That's no problem. From 0 to b. And my f of x was e to the negative x over 2 with respect to x. And so because b is infinite, it's not a set number like 13, right, or 17 thirds. We want it to become infinite. We set this up as a limit expression. Well, I've got a good feeling about this. We just spent, right, a full day practicing our integration techniques. Can we find an antiderivative for e to the negative x over 2? Yeah, we've got the derivative of the exponent. That would just be negative 1/2. And we'd have to cancel that out with a negative 2, and then the exponential itself. So I think we're fine. So we keep our limit. And we would get an antiderivative function. It would be negative 1/2 times, so negative 2 e to the negative x over 2. Is that right? And we'd evaluate that from 0 to b. And consider the limit as b goes to infinity. Okay. So the limit as b goes to infinity of, and this evaluation would become negative 2 e to the negative b over 2, right? The upper limit all the way through, minus the lower limit all the way through. Well, that's minus the negative 2, so I'm going to make it plus a positive 2. E to the negative 0 over 2 is just 0. So we've evaluated our definite integral, right? And now all that remains is considering the limit as b goes to infinity. Let's investigate that quantity. As b goes to infinity, what's happening to this first term? Well, this is negative 2 over e to the positive b over 2. Yes? So I think we've got a good shot here. And e to the 0 is 1. So what happens to this fraction as b becomes infinite? Well, thank goodness for Bellwork, right? We see that e to the x, as x goes to infinity, becomes infinitely large. So negative 2 over infinitely large shrinks to 0. And we can evaluate this exactly. Our tool is the limit that allows us to do that. This term goes to 0. And the limit of a constant is the constant itself, which means that while the first quadrant stretches forever and x goes to infinity, the area underneath that curve is finite. It exists and is exact. Not only that, but it's an integer. This is nice and pretty. Right? So the exact area in the first quadrant is 2. How cool is that? And so the area underneath this curve, right, in the first quadrant is 2. I'm going to go ahead and put an all caps yes, because that was pretty sweet. We'll see that sometimes, right, we'll be able to evaluate what we'll call an improper integral and get an exact answer, like 2. Other times, we'll not be able to evaluate the improper integral, right? And we'll have what we call it, the integral diverges, much like when we were talking about sequences and series earlier in the year. And so we could have an improper integral that converges, in which case the value of the improper integral would be finite and it exists. Or if the value of the improper integral does not exist or is infinite, then we say the integral diverges. We wouldn't be able to find, in this case, the exact area. All right, so here we've got some notes. Our improper integrals, right? An integral is said to be improper if one or both of the limits are infinite. We saw in our first one that the b was going to infinity. So we were trying to figure out the limit of 0 to infinity, right, for my limits. So we set up a limit. One of my limits was infinite. An infinite discontinuity occurs at an endpoint, and so if one of my endpoints is like a vertical asymptote, right, where my function values shoot off towards infinity or negative infinity, we still may be able to determine the exact area underneath the curve. We might not be able to. So the improper integral may converge or diverge. Or if there's some infinite discontinuity of vertical asymptote in the middle of A and B, right? And so if we've got a vertical asymptote in between my limits of integration A to B, then it could be an improper integral. Again, it could exist. Even though there's a vertical discontinuity, the improper integral could converge, and we could be able to find its value. All right, so this is what I was rushing to get printed out on Thursday before break, and so your intervals here don't match the examples, and so you'll have to rewrite the intervals. So the first case, we're letting the upper limit go to infinity. So if I've got a continuous function f on the interval a to infinity, then in trying to evaluate the integral from a to infinity of f of x dx, our tool will be the limit. So I'll let b go to infinity, my upper limit go to infinity, and try to evaluate this improper integral. So we'll let the limit as b goes to infinity of a to b, which I know how to evaluate, of f of x dx, and that's exactly what we did in Bellwork. I'm sorry, that's exactly what we did in our warm-up problem. Next limit, you guys need to rewrite. Suppose that my function is continuous on negative infinity to b. If my function f is continuous on negative infinity to b, I'll try to evaluate that improper integral, the integral from negative infinity to b of f of x with respect to x, by letting my lower limit, in this case a, approach infinity. Because I know how to evaluate, right, the integral from a to b of f of x with respect to x. And lastly, rewrite your limits. Where did I go? It should be negative thing. Sorry. Talking, writing, hard. Thank you. That was my mistake. And that's an A. Not 9. And lastly, if my function is continuous on negative infinity to infinity, even though those are not actual numbers, we can still consider the value of this limit by letting the top, right, and the bottom go to infinity. In order to do that, we'll go ahead and pick any constant in between. It could be any constant in between. I'll call it C, right, and evaluate 2 separate intervals and then sum them together. And so we could let the top go to infinity, we could let the bottom go to infinity, but we'll break it up first. So what I'll do is I'll say the integral from negative infinity to c of f of x with respect to x, plus continuing on from c to infinity of f of x with respect to x. And lastly, I can now consider two limit expressions just like the top. So this time I'm going to let my lower limit a go to negative infinity. And now consider the definite integral from a to c of f of x with respect to x. And now we'll consider the second limit separately. This time we'll let our upper limit, right? Our upper limit go to infinity. So I'll let b go to infinity of c to b of f of x with respect to x. So we're relying on some of our definite integral properties that we developed last year in AB. In other words, we can break this up, right, into a sum of individual integrals by picking any constant in between, negative infinity and positive infinity, and that's all we did in the first step. And then we used our limit idea from the first one and our warm-up to complete the statement. Now we'll see how each of these looks like in context. Okay, so we'll take a look at each of these three cases. All right, so if this limit exists and is finite, the improper integral converges, and this limit is the value of the improper integral. If the limit fails to exist, right, that is, it's infinite or does not exist, then the improper integral diverges, and we can't find its value. It doesn't exist. All right, so let's go ahead and consider something. Again, we'll be using our graphing calculator to consider the graph and see what it is that we're trying to find. We're trying to find the area in between 1 and infinity of the graph 2 over x. So let's go ahead and take a look at this. Everybody on your calculators, let's rewrite my y equals function to consider the integrand function 2 over x. And I think I'm going to make my upper y value 3.25 just to get a nice picture. And I don't know if that is good. That's okay. Does everybody see what we're trying to find? Right? We're trying to find the area in between the curve and the x-axis from 1. So here's our starting point. We want to start here to infinity. Right? Does everybody see what we're trying to do here? Okay, so what is the giveaway? We have an improper integral? Yeah, we got the infinity as one of my limits, so it's an improper integral. But that's okay, because we got a tool bag, comma, baby. We worked hard to develop it. In this case, our tool is the limit. Right? We're going to rewrite this using a limit. And so let's go ahead and consider the limit as b goes to infinity of 1 to b, because we can evaluate that. So can we find an antiderivative for this integrand function? Absolutely, right? 2 over x integrates to 2 natural log absolute value of x. Yes? So we'll go ahead and try to evaluate the limit as b goes to infinity of 2 natural log of absolute value of x evaluated from 1 to b. Okay, well that would equal the limit as b goes to infinity of 2 ln absolute value of b minus 2 ln absolute value of 1. Right? That is my upper limit into my antiderivative function all the way through, minus my lower limit into my antiderivative function all the way through. Yes? Yes? Okay. And as b goes to infinity, well, ln of 1 is 0, so this is just 0, right? This whole quantity is just 0. You guys see that? What about this first quantity, 2 natural log of b? What happens to this quantity as b goes to infinity? It become 2 ln of infinitely large, right? 2 ln of infinity. And as natural log function goes, as x goes to infinity, ln of x also goes to infinity. So this is infinite. Remember, if this is infinite, right, this is going to infinity. If this is infinite, then the improper integral, right, does not exist and is said to diverge. So while the first one, we were able to find an exact area and it equaled 2 was very nice, this one, it goes on forever, continues adding and adding and adding and adding more and more area, right, such that we cannot find the exact value, right? This improper integral diverges. So since this does not exist, or is infinite, we say that the improper integral diverges. We can't find its value. It does not exist. Much like a series that diverges. All right, so we've seen an example where, gosh, they look similar, don't they? I'm trying to find it. I mean, don't they?
Yeah.
But even on this window, I kept the same x-axis, -1 to 10. What do you notice about my function values as you just even get to 10, right? In this picture, everybody looking? In this picture versus this picture. See how this is like just a little bit taller still, and I even made my scale a little bit. So there's going to be some sort of balancing point, right, where I'm adding up a small enough area forever that I can get it converges to an exact value versus adding up too much, right? Too beaucoup, too much, and I'm not able to find the exact value of the area. That's interesting to me. All right, let's take a look at another. Again, we're going to use the graph for inspection, then we'll evaluate analytically. So let's go ahead and consider this one. We've got 3 over x squared, and this time we need to go a little bit bigger, so let's do 3 over x squared. And I'm going to go maybe up to now 4.25, 5.25. And we'll see what that looks like. Okay, and so again, we're starting at x equals 1. So we're starting at x equals, oh, I can't draw it quite yet. Gut feeling, right? I mean, this is the 3rd time we've seen this. But, right, it looks like we're getting kind of scrunched down here more than the middle and the divergence. So let's go ahead and see. All right, so you guys ready to do it? I'm going to go ahead and I'm going to pause the recording and I want you to try with your partner because you get the setup. Okay. Yes? I'm going to go ahead and pause the recording and let you guys try this one. Okay, ladies and gentlemen, at this stage, you and your partner have had a chance to try and evaluate this improper integral by using limits as our tool. So we've rewritten my upper limit, b, right, as b, and we're going to consider the limit as b goes to infinity. Raise your hand if you have the antiderivative function -3 over x. Evaluated goes to -3 over b plus 3 over 1, and we consider the limit of this expression as b goes to infinity. What happens to this first term as b goes to infinity? Riley?
It goes to 0.
It goes to 0. So as b goes to infinity, this first term approaches 0, and the limit of a constant is the constant itself. By golly, I'm getting a limit that converges. I'm getting an exact area here, even though we let x go to infinity, right? We're still getting an exact value of 3. Raise your hand if you got 3 already. You got 3? Yes, that's awesome. Awesome. Great. Okay, so what's tricky? Well, let's go ahead and consider now what happens when we consider the graph of 2 over x squared plus 4x plus 3. So we're going to go from 0 to infinity this time. I'm going to adjust my window a little bit. Let's consider a new function that is 2 over quantity x squared plus 4x. What's going to happen there? When I see a rational function, I get nervous, right? Because I think of vertical asymptotes. And so I think this rational function has not 1, but 2 vertical asymptotes. Yes? If I were to zoom 6 on this bad boy, I'm going to have 2 vertical asymptotes. That factors to x plus 3x plus 1. But on the bright side,
What area are we in?
right, both of those vertical asymptotes are over in the negative x values, and this limit is asking about 0 to infinity. And so do those vertical asymptotes affect our definite integral? No, they don't. And so I think we're okay. I'm going to go ahead and readjust our window now to go from maybe 0 to 1 for our y values. So we'll go -1 to 10 again, but let's just go -0.25 to 1 and see if that makes a nice picture. So there comes our rational function, and hard to tell, but it does look like it, right? The function values get down close to 0, so it's possible that this infinite sum of areas does exist, right? But we don't know. So what are we going to do? We're going to reach into our algebraic tool bag, duct taped and pattern worn though it may be, and we're going to grab onto our limits as a tool. So let's rewrite this improper integral as a limit expression. And let's consider the limit as b goes to infinity of the integral from 0 to b of, sorry, I'm saying out loud when I was thinking it, and I'm saying it out loud too. Because what? What's the problem? Well, I can't use natural log here.
That's okay.
Why, Sid?
We'll get there.
We'll get there. Sid's telling me.
Yeah.
Yeah, we don't have the derivative of the top, or sorry, the derivative of the bottom present, so we can't use natural log, and it's not in our standard because of linear, but we can use partial fraction decomposition here where we're at that bottom fully factored form. It just means that we're going to have to, right, do a little algebra first. So once again, I'll break in with my brackets just to rewrite my integrand function, then we'll close our brackets and then rewrite our original. So let's go ahead and rewrite that. I know that I could rewrite this complex fraction, right, as a sum or difference of individual simpler fractions using partial fraction decomposition if I could just factor that denominator. And so what did you get for your factorization of the denominator? Grace?
X + 1 and x + 3.
X + 1 and x + 3. Awesome. I know that must be given by a over x + 1 plus some constant b over x + 3. Great. So this first fraction would need an x + 3. Good, good, good. Plus the second fraction would need an x + 1. And together that must equal the numerator 2. Convenient x value, I'm going to let x equal -3. Then the first term drops out, and b times -3 + 1 is -2. So -2b equals 2. So b must equal -1. And by letting x equal -1, so we're gadget arm, then the b term drops out and I get -1 + 3 is 2, 2a. 2a equals 2, which means that a equals 1. Yes? Awesome. So algebra is done. And I can rewrite my original now as a limit still as b goes to infinity of the integral from, bless you, 0 to b of, oh my gosh, what do we find out? It's given by 1 over x + 1. Minus 1 over x + 3. With respect to x. Is that right? Did I get it? Cool. Can we find an derivative from an integrand function? You bet your boots we can. This is given by the limit as b goes to infinity of natural log of absolute value x + 1 minus natural log of absolute value x + 3 evaluated from 0 to b. Is that right? Okay. Let's do one more, guys, to get it done. I think we're going to need actually 2 more, but I'm going to go for it all the way through. So here we go. ln of b + 1 as b becomes infinite, this is going to be positive, so I'm going to drop the bars now. Minus ln of b plus 3. Minus ln of 1. Minus ln of 3. So minus a negative ln of 3 is plus ln of 3. Right. So what have we got? Well, we've got two natural log expressions, right, where the input, which contains b, is ballooning to infinity. All right, that's bad news because we saw in our second example when we had 2 ln of infinite quantity, that equaled infinity and that diverged. Right, that diverged. But I do have ln of infinite minus ln of infinite would kind of be like infinity minus infinity, which should be jogging your memory as our indeterminate difference. And so let's use the properties of natural logs to rewrite that as a single natural log and see if that doesn't help us. That is to say, a difference of individual logs can be rewritten as a single log of a quotient where it's first over second. Let's see if that helps us. So I'll rewrite this as ln of a quotient, b plus 1 over b plus 3. Yes? Ln of 1 is 0, so I'll forget about that, plus ln 3. Guys, we're closer, right?
We're not there yet?
But we're not there yet because look, I'm getting infinity over infinity as my input, right? As my input. And so because I'm evaluating a limit, technically, right, we can use our function interchange theorem to do the limit of natural log is equivalent to the natural log of the limit so long as we're continuous at our input. Or we could do our algebraic trick here of dividing top and bottom by the largest power of b that appears in the denominator. That is to say, I really could rewrite this as, we did it once with our sequence series. If we just divided each term here by b, we multiply by 1 over b, we'd get ln of b times 1 over b is 1 plus 1 times 1 over b is 1 over b. All over b times 1 over b is 1 plus 3 times 1 over b is 3 over b. Sydney, stay strong. Also that we could say what? Well, Riley just told us that 1 over b, as b goes to infinity, goes to 0. 3 over b goes to 0, which means I get ln of 1. Does ln of 1 exist?
Yes.
Yes. What is ln of 1? Plus ln 3? As b goes to infinity, this expression exists, it converges, and it equals the natural log of 3. No absolute values are needed because we know my input is 3. That was pretty awesome. So we did look at that once in our sequences and series for multiplying or dividing by the largest power of my variable that appears in the denominator. So what did I do? Here the algebraic trick was times 1 over b by 1 over b. So I was multiplying by a clever 1. I can write that in here. Should I write that in?
Yeah.
Good thing you're oriented, yes. That's pretty sweet. Ah, the beauty of calculus. You know it's been a go-go gadget arm page when we got all this gray on the sides, huh? Let's take a look at number 4. So, our graph will give us an indication of what's going on here initially, and then we'll take a look analytically. So, I'm considering a new integrand function. In this case, we want x times e to the negative x. And we're going 1 to infinity. And I'm going to let's see what this graph does. Interesting. And so, as we're close to the origin, it looks like this behaves a lot like the linear function x to the first, but But then, as we get farther and farther away, the exponential term overwhelms it, right? And it looks like it's pulling down the value towards 0 as x goes to infinity. Defined for all inputs, and so this is domain negative infinity to infinity. Let's consider this problem. The integral from 1 to infinity would start here and start summing up area, yes? Okay. So, gut feeling? Well, it looks like it shrinks down towards 0 for function values, and so we could certainly see how this could exist, right? Now, I don't know that it does or not, but we could see how it could because it looks like my function values are shrinking down towards 0, so the area accumulated might be small enough such that the infinite sum, right, converges to an exact value and we can find it. But I don't know yet until we do a limit. So let's go ahead and set up this improper integral as a limit, as one of my limits goes to infinity. So I'll grab this. I think this is so cool. You know, that's pretty awesome. So we'll rewrite this as, you're like, first day back. 4 cups of coffee, like this, friends.
So shaking my head. So we review day. Calm down.
Just think, that's on the back burner though. That's this class.
Oh, almost there. Review
Alright guys. So what do you think? Can we find an antiderivative function for that integrand function?
Absolutely.
What will we use to do that? Yeah.
What is that?
We've got 2 distinct parts in my integrand function, but one is not the derivative of the other, right? So this is not a situation for u substitution or undoing the chain rule. This is a situation for integration by parts, liate. Thank you, Tyler, baby. Liate, right? Where we'll go ahead and do an integration by parts problem. After that last Go Gadget arm page, I am surprised we have any room. That's the beauty of digital smart board. All right, so Tyler tells us Liate assigns priority for our integration by parts. Who gets U? Well, we got algebraic and exponential. So who's going to get the U assignment? Algebraic, so let's go U is X. Then the remaining part of the integrand, all of it has to be the dv, because we need everybody represented. So e to the negative x dx, are you guys good? Which means the du is 1 dx. And b is what? Can we find negative e to the negative x?
Nice.
Totally going to do this. Dude, totally going to do this. So we have the limit as b goes to infinity of the integral from 1 to b of, and now let's do our integration by parts. I know the antiderivative of u dv is given by what? U times v minus the integral of v du. So let's go ahead and rewrite that by parentheses. So it's given by u times v, that's negative x e to the negative x, minus the integral of v du. Hang on, I don't want to do this anymore. But don't worry, I still... I still have 1 to b here. Ready? U times v minus the integral of v du. So I'm going to do minus and negative is plus a positive e to the negative x dx. Was that helpful? Well, it's not the prettiest looking expression, but by golly, we do know an antiderivative rule for this integral. So yes, integration by parts was useful in this case because we have an antiderivative for this new integral. So we get the limit as b goes to infinity of negative x e to the negative x. Antiderivative for e to the negative x is negative e to the negative x. Evaluated from 1 to b for both. Can we do that? Grace?
Really, I tried to remember this from 1 to b of e to the negative x. Why isn't it negative e to the negative x? Because isn't it du times v?
Right here?
Yeah.
Yes, it is. Yes, it is u times v. So my formula is the integral of u dv is u times v minus the integral of v du. And so what I did, Grace, was did minus and negative.
Okay.
So plus and positive. That's what that plus means. Is that good? Is that right? Okay. So what's up? Can we evaluate this expression? You bet your boots. Let's keep this as the limit as b goes to infinity one more time. And now let's plug our upper limit all the way through. So I get negative b e to the negative b minus e to the negative b minus all the way through. 1 goes to negative 1 e to the negative 1 minus e to the negative 1. And we want to evaluate the limit as b goes to infinity of that whole shebang. Let's go term by term, you guys. Recall that e to the negative b is the same as 1 over e to the positive b. So what's going to happen to each of these terms, right, each of these first two terms, as b goes to infinity?
0.
0. So this goes to 0, this goes to 0, which means I'm left evaluating a constant minus a constant, which is the constant itself. So I'm getting negative 1 over e minus 1 over e is negative 2 over e times the negative out front. I'm getting in 2 steps positive 2 over e. Once again, opposite of negative is plus a positive 1 over e, plus a positive 1 over e is 2 over e. Are you guys, I need to write a minute in the middle, or are we okay? That's pretty sweet. Dang. Yes?
Can you go through again why it goes to 0?
Right here? Absolutely. So I happen to have a go gadget on, Grace, at my disposal. So check this out. We know that e to the negative b is the same as e to the negative b is the same as 1 over e to the positive b. So each of these terms has a e to the b on bottom, which will overwhelm that b or the 1 on top. As b goes to infinity, this exponential term goes to infinity, and a constant over infinity, right? Right, that's going to go to 0. So I blame Riley. Don't blame me, blame Riley. He told us that earlier. Good? Good? So, I feel like, yes.
Okay, but if it's negative b over e to the b, then wouldn't it be negative infinity over infinity?
Yes, it would be. It would be. And I was banking on the fact that, and that's indeterminate. I was banking on the fact that this is a linear over an exponential, and we could do L'Hopital's rule, and the derivative of that linear b would be a constant 1, negative 1, over still e to the b, still infinite. And so whether this is positive or negative constant, a constant over infinity still goes to 0. So yes, I kind of wrapped in L'Hopital's rule right there, just because we had our linear to the first versus exponential wins. Are you guys okay with that? Because we could do a L'Hopital's equals h, one step. Okay? All right. So I feel like, what haven't we dealt with? Well, we've gone ahead and let our upper limit, right, go to infinity. We haven't considered when both of my limits are infinite. So we'll take a look at one more, and then I think what we'll do is we'll scooch some of our practice into Thursday's review day 2. And so we'll hold off on one thing here with our Bird class and book. So what I want to do is just consider this one together. As we consider this function, we're extending our domain and our interval to be infinite. We're going to go from, in this case, both directions. negative infinity to infinity. So let's go ahead and take a look at this picture again through inspection, and then consider this improper integral analytically. So everybody, let's get a new y equals. What? 1 over quantity 1 plus x squared. What does this even look like? Well, x is 0, and then it gets bigger and bigger. I'm going to change my window. Y max was 1. So I'm going to go to 2 for my y max and see if that helps at all. And I'm going to go negative 10 to 10. So did I get all my double clicks out of the way? Riley, you're kind of in charge of that. I don't know why you're not saying anything. So what happens here? Does everybody see this function? So it looks to me like y approaches 0 as x goes to negative infinity and as x goes to positive infinity. And furthermore, because I made my scale just to 2, it does look like it scrunches down. And so we've seen just through inspection and informally that if it's kind of tall here as you're getting, farther out, then that diverged. But when we were going to scrunch down here, we saw that oftentimes it did exist and converge to an exact value. The question is the fact that we're considering both sides going to the infinities, right? Is that going to add on too much more area so that now it's infinite and it doesn't converge to a particular value? You see what I'm saying? Because now we're letting both sides go to infinity. So what's our tool? Well, our tool to evaluate this improper integral is now going to be with limits. So we're going to use limits to evaluate this. So how are we going to do that? Well, we've got a couple different things to deal with. Firstly, right, I've got both upper and lower limits are infinite. And so I'm going to have to break this improper integral up, right, at a convenient constant. Is there a convenient constant where you'd like to break this up into 2 halves? 0. So let's go ahead and rewrite my original as negative infinity to 0, and then plus 0 to infinity. So we'll have 2 separate, right? Where now only one of my limits is approaching infinity. And then I'll be able to evaluate. I'm down. So let's go ahead and first rewrite this as negative infinity to 0 of plus the integral from 0 to infinity of. You guys okay? Great. So how is that helpful? Well, because now I can go ahead and do 2 separate limits. Now I'll do the limit as a goes to negative infinity to 0 plus the limit as b goes to infinity, right, from 0 to b. Great. Yes? Because we know how to evaluate the limit. We know how to evaluate the integral from 0 to b of f of x with respect to x. Can we do that? Yeah, let's do it. Antiderivative function for 1 over 1 plus x squared. Inverse tangent, baby. Inverse tangent. So inverse tangent of x from a to 0 plus the limit as b goes to infinity of the integral of, nope, inverse tangent of evaluated from 0 to b. Oh gosh, I think we need a couple more still. So this becomes inverse tangent of 0 minus inverse tangent of a, and I need the limit. As a goes to negative infinity. Plus the limit as b goes to infinity of can fit. What? We can fit. Inverse tangent of b minus inverse tangent of 0. I thought we could fit. We can. We can pause it. Group it. We can fit. Do we fit? Come on, closer. All right. So what happens in this first term? Well, the inverse tangent of 0 is asking for the angle whose value of tangent is 0. Is there an angle in between negative pi over 2 and positive pi over 2 where the value of tangent is 0?
Yeah.
What? 0. That's a constant. So the limit as a goes to infinity, constant is constant, minus. As a goes to infinity, this is saying what's the value of an angle that's going to infinity? What? Where tangent is going to infinity. Wait a minute. Tangent goes to infinity, right? An infinite number of times, but in between 0 and pi over 2, when does tangent approach infinity? As x approaches, because this is a limit, I can evaluate this, and this is minus pi over 2. Solid. Solid. I want you on my team. Again, oh, that's negative infinity. So negative pi over 2. So that's minus negative pi over 2. So that's plus pi over 2. Yes? Now, this one was infinity. So this one's positive pi over 2. Yes? Minus an angle in between 0 and negative pi over 2 0. Hey, guys. I think this converges. How come? Because pi over 2 plus pi over 2 is equals 5. That's pretty bomb. So moral of the story, yes, that area exists and it is finite despite the fact that both limits, not just one, were infinite in this case. Courtney.
Could you find the area under the curve from 0 to infinity and just multiply that by 2?
Yes. Because it's an even input, we could use our properties of definite integrals back from AB, where the integral from negative a to a of an even is twice the integral from 0 to a, right? Yes. So you could use the symmetry of the graph to do that.
Okay.
And that would have been one infinite limit, one limit instead of 2. That's a great idea. It would have been way quicker. Nice.
Oh.
You still have to use the limit though with your notation. Good. Awesome. All right. So what we're going to do is we're going to hold off on this where I have infinite discontinuities. We'll include that in our discussion. So we will have a part of a lesson, right, which will be probably less than first half, and then you'll have some review time in class, and then we're setting up still test on Monday. What we're going to do is we're going to pause this right here. So we're going to stick to this because we have enough for this. So what criteria make an integral improper? And when evaluating an improper integral, how does one know if it converges or diverges? Please be ready to share because I'm going to call on you, but I'm going to modify the assignment. Okay, ladies and gentlemen, there's 3 different criteria that could qualify an integral and make it improper. So what's one thing that would make it an integral improper? Kobe?
0 of the limits are infinite.
Yes, well that takes care of a couple. So if one of the limits is infinite, so if one of my limits of integration is infinite, in infinite, that's how I do it too. Great. What else would qualify as improper that we'll have to look at closer next time? Sophia? Good. If we've got an infinite discontinuity, that's synonymous with a vertical asymptote. So we got a vertical asymptote. As a limit. And the last one also indicates that, Marissa?
If there's an infinite discontinuity anywhere on the interval.
Absolutely. So what I'm going to do is piggyback and say if there's infinite continuity as a limit or in the interval. and then I get all three in the interest of time. Awesome, thank you. When you evaluate an improper integral, how does one know if it converges or diverges? So how do we tell whether the improper integral converges or diverges? Danny?
If it like goes to infinity, that means it diverges, but if it like goes to value.
Good. So if limit is infinite or does not exist, then the improper integral diverges. If the limit is finite and exists, then the improper integral converges to that value. Oh my goodness gracious. And who could have asked for better timing? Modified assignment. So we've got page 475, 1 through 23 odd. You guys didn't have this anyhow, right? Good. So this is now out of 12, okay, instead of 16 problems before. Way too much. So this is 1 to 23 odds on page 475. Feel free to share with your group chat, and I'll go ahead and export the notes.